Hello everyone, welcome back to our machine learning course. I'm Joaquin van Schoren, and this lecture will be all about neural networks for text, or how we can convert a selection of text into a selection of numbers that maintain the same information or the same semantics. As a short overview, we'll first talk about the simplest way to represent text as numbers, called the bag-of-word model. Then we'll talk about word embeddings, which are lower dimensional representations of text, of words. First, we'll talk about how we can learn our own word embeddings given a certain task. And then we'll talk about how we can use a pre-trained word embedding that was trained on a different, larger task and then transfer it to our new task to learn better. Then we'll see how we can use these embeddings inside larger neural nets. And then we'll talk more about how we can apply them in practice. Let's look at a real example. This is some examples from the IMDb review database. So it's a database of movie reviews, and we want to predict whether they are positive or negative. These are a few examples. Like for instance here, the review says, this film is just brilliant, blah, blah, blah. This one says, it begins better than it ends. This is more negative. And this one is more balanced. The French horse cinema has seen something more revival, blah, blah, blah. Okay. Now, this is the text we have. Now, you can see that this is already processed. First of all, it's all lowercase. We removed all punctuation, like there's no dots in the text anymore, and so on. But that's about it. So otherwise, it's still fairly truthful to the original text. Now let's see how we can represent that using bag of words. So this is how this will be encoded. So this is review number 3. And first of all, we have to construct a dictionary, which already has been done for us. In this case, this has 88,000 different words. Now we want to use those. So every word here is now replaced with a number. And typically we order the words in the dictionary by how frequently they are used. The word the is apparently the most frequently used word, so that has number 1. Scots is much rarer, so it has a much higher number, and so on. At, again, very common, has a lower number. So the basic idea is every word is represented as a number. So now our text becomes a string of fairly meaningless numbers, right? The numbers themselves don't have meaning other than relatively globally how common these words are. Now we represent this in a bag of words presentation, which means that we will put a 1 if the word occurs, right? So the word the occurs, the second most common word occurs, and so on. So now we can already start building classification models. So what we basically did in the previous slide is we built a giant matrix with about 20,000 columns, each column corresponding to a certain word, like the word the, or the word perfect, and so on. And in the rows, we have all the documents. So document 1 or review 1, document 2, and so on. If we use a one encoding, this will be a matrix with just zeros and ones. And so we can actually store this as a sparse matrix, which is good because these matrices can get pretty large if you have a large number of documents. Like sometimes you have hundreds or millions of documents. Like if you represent tweets, you'll have billions of tweets perhaps. Right? And you will still have 20,000 or even more words. So this will be a gigantic sparse matrix. Right? And it's nice if you can store this as a sparse matrix. You don't have to fit everything to memory. So that said, we now have a table, and we now can train any machine learning model on this. So in this case, this becomes our features X. We'll have a corresponding value Y, in which we'll have like positive if the review positive or 1 if it's positive, and 0 if it's negative, and so on. And we can just give this to our model. Any model we have, we can just fit that with the X and Y data. Okay? That's it. So this already works quite nicely. We have about 85% accuracy in predicting whether the review is positive or negative, which is great because we didn't do much, right? We just represented the text with ones and zeros, and we already get a decent performance out of it. Now we can also introspect what the model is learning. So remember that every column here is a feature. Every feature corresponds to a word, right? So in our model, we have a feature for the word the, we have a feature for the word poor or movie or perfect, and so on. Right? And every coefficient in logistic regression, which is a model we used here, will correspond to a coefficient. And we can look at the coefficient's values to see how the model is using these words to make predictions. So if you plot this here, we see that the most negative coefficients, so these are the coefficients, values, right? The value of the coefficient. The most negative coefficients correspond to words that happen to be describing bad things, like worst or awful or terrible, while the most positive coefficients correspond to words like excellent or wonderful or perfect. Okay, so we see that whenever the model sees a word like worst, it will be more likely to predict that this review is negative. If it sees words like amazing or outstanding or perfect, then it's more likely to predict that this review is positive. Okay. Now we can do a lot of preprocessing to get to our array of ones and zeros or other numerical representations. So the first thing we need to do is tokenization, which means we take a string and we convert it into individual words. Now you can decide, like if you have a string like do you want ants, we can decide to just split on spaces. Do you want something like breakfast, right? Then maybe we have a hyphen in there. And we need to decide whether we want to split on this hyphen or whether we do something more clever and join these words together again. Sometimes you can have things like apostrophes, like at Tiffany's. Right, and so we have an apostrophe. We may need to decide whether we ignore that or we keep that apostrophe as a letter or whether we split the word. So these are all decisions that you need to make in tokenization. Now these days tokenization is fairly standard, so you can use libraries like NLTK, Spacey, Jensen, and so on to do this tokenization for you, and it really have pretty good trade-offs for this. The next thing you want to do is stemming, which means that if you have a word like meeting, it can come in different representations, right? You can have meeting, or you can have meet, or you have met, or meets, right? So all these variations, you can choose to, and these variations typically represent the same thing, or the same semantics. So what you want to do typically is to do stemming, so meeting becomes meet, and meets becomes meet, and met becomes meet, right? So that you have one word to represent all these things, and if you have fewer words, the model becomes easier to learn, of course. Okay. So stemming is it's kind of a no-brainer. You should do this. Right? Now, stemming, the concept stemming corresponds to the naive way of doing this, right? Just having a dictionary of stems and variations like plus ing, or plus s, or plus ed, and so on, right? So you can do this naively. Lemmatization is a more intelligent way of doing that, which is based on NLP. So what NLP does, this stands for natural language processing. So what this does, it will look at the sentence that this word occurs in. For instance, if you have a sentence like, let's go to the meeting, then meeting will be labeled as a noun. And then it decides, well, we can indeed maybe we keep this as meeting because meeting is the noun. And we map only meeting and meetings to the same word. On the other hand, if you have a sentence like, are we meeting? Then the NLP will say, well, this is a verb. And I will match it to stuff like met or meets or other variations of the verb to meet. Okay, the meet itself, of course. So lemmatization uses NLP to do this studying or lemmatization in a more intelligent way. Another thing you typically want to do is discarding stop words, such as the or an. These occur in any text, and so they don't tell you anything about the text really, so you might as well just remove them. Another common trick is to only use the most frequent words. If you have an infrequent word, like maybe Tiffany's, right? It's a very uncommon word, and you may want to ignore that in the text because because the word is so rare, it doesn't often occur in text, and so there's not much to learn from. Right? If this word only occurs in one text, the model is unlikely to actually learn from that unless it overfits. They don't want that. So it's typically a good idea to then skip those very infrequent words and only use, for instance, 10,000 most frequent words. If you have an exceptionally large vocabulary, for instance, if you want to analyze a large collection of tweets, you may not have 20,000 words, you may have millions of words. And in that case, it may not be the best thing to just use the 10,000 or 20,000 most frequent ones. What you can do in that case is you can use a has function. So has function typically has something like, you can have like 100,000 bins or maybe a million bins, right? And every word is mapped to a certain bin. Now it's possible that you have collisions, right? That, for instance, the word Tiffany's and the word lambda, whatever, occur in the same bin. It's possible. These collisions are typically quite rare and they don't harm so much the performance of your model, the predictive performance of your model. But what it bites you is that you can now have control over how many words you need to put into your memory. And you can decide this based on your infrastructure, whether you can handle, for instance, 100,000 words, then you use 100,000 bin has function. Right? If you can use a million, you can use a has function with a million bins and so on. Okay. Another very frequent thing to do is to use anagrams. Anagrams are collections of and adjacent words, like awesome movie, or movie with, or with creative. So if you have a sentence like, it's an awesome movie with creative design, then you would not split this into awesome movie with creative, but you would actually create, in this case, bigrams of 2 words or trigrams of 3 words that occur together. And so that is some way that you can still maintain some of the word ordering into your bag of words. If you don't do this, then the word ordering is completely destroyed by the bag of words presentation. So bigrams help you maintain some of that information. Another thing you can do is character anagrams. So in that case, you do the opposite, basically. You take words of and adjacent letters. A word like awesome does not get mapped to the term awesome, but get mapped to all the collection of three continuous letters in the word awesome, like awe, with, saw, and some, and so on, right? What this buys you is that you don't have to deal so much with all the possible variations of words, because even very infrequent words can get mapped to quite frequent character anagrams. Right? So if you have another word like Tiffany's, which is rare, you would map that to tiff and if and so on. And these anagrams may be more common because they occur in other words as well. Right? So it's a better way to represent rare words. Now, of course, you can again have a huge amount of possible letters. So you don't only do this for 3 grams, but also for 4 grams, 5 grams, 6 grams, typically. So you end up with a lot of n-grams, and you typically want to then use a hash function again to control the number of n-grams you want to store into memory. Okay. Now, all of these things are packaged fairly neatly in libraries like LTK and Spacey and so on. So you typically have functions you can just call do this for you. You just need to decide based on your problem, based on how many words you have, how large your collection is, which of these tricks you want to use. The next thing you want to do is scaling. There's different ways to do that. The simplest way is L2 normalization. What this means is say that you have a vector of counts for every term ti, then you divide every one of these values by 2 norm of the entire vector of counts. Right? L2 is just the root of the square sum of all the values in the vector. And what this does is that the sum of the squares of all these scaled values will equal to 1. We've seen this in the course on preprocessing. It's called the normalizer, and it does exactly this. The reason why we do this is that normal Euclidean distance is not good in high dimensions, not very useful, because every distance between any 2 points will be more or less the same if you have a very high dimensional number of dimensions. In that case, you want to use something more akin to cosine distance, right? Which is more meaningful. But cosine distance is not so easy to compute. So the easy way around this is to simply normalize the values of your vector, and in that case, the Euclidean distance is equivalent to cosine distance. It's a very nice trick to get meaningful distances in high-dimensional spaces. And you definitely want to do this whenever you want to use a distance-based model such as KMN or SVM. Another very popular technique is term frequency times inverted document frequency. And this rescales the frequency or the counts of your terms in the document depending on how often it occurs in other documents. The basic idea is that if you have a very rare word that only occurs in this document, then you should give it a higher weight, while a word that occurs in all documents, like the or an or something else more common, you should give it a lower weight because it's not very indicative for this particular document. Right? And so you take your original frequency of your word and you multiply it by the log of n, the total number of documents, divided by the number of documents in which the term ti occurs. Right? So if the term ti does not occur in any other document, then this will be a large term. If it occurs in all documents, this will be a very small term, and you reduce the value of that term. Now, normally you do these steps in preprocessing, so you can use a scikit-learn normalizer, or you can use a TF-IDF transformer. If you can also do this in layers in TensorFlow, there's a lambda layer which allows you to use any function, to apply any function on the input. For instance, you can apply the normalizer function on the input using a lambda layer. There's also a token vectorizer or string vectorizer in Keras, which does a lot of things, including scaling. Okay, so for now, assume that our words or our text is already processed, and we can now want to build a neural network based on representation. Right? So in this case, I assume we'll have a one encoding using the 10,000 frequent words and dropping the top three stop words like the and so on. Okay? And now we can already start building a simple neural net. Right? So what we're doing here is the same as using logistic regression, but now we replace logistic regression with a small multi-layer neural net. We have two layers here. So the input shape is a 10,000 dimensional vector, right, of ones and zeros. And we'll have one dense layer of 10 nodes, another dense layer of 10 nodes, level activation. And then because at the end we want to predict whether the view is positive or negative, we end up with one output layer, right? So if you look at this, we have an input layer of 10,000 possible values, zeros and ones typically. Then we have a layer of 16, another dense layer of 16, and our output layer only has one output, which then, of course, has to be one if it's positive and zero it's negative. Right? And we use binary cross entropy as loss function, and we backpropagate the weights. We learn all these weights here so that you can learn the mapping from any text to an output of 1 or 0. Okay? Of course, because we have a numeric output here, we use the signal activation function. Okay, let's see how that works. So here we take a validation set of 10,000 samples and we train on the rest. And we see that, well, we get an accuracy, validation accuracy by 88, which is slightly better than logistic regression. Right? Logistic regression had 85%, now we have almost 89%, so it's a few percentage better. We do see that it is good until like epoch 4 or 5. Weight regularization, right? So we add our L2 regularizer with alpha 0.001. If we do that again, we see that well, it overfits definitely less. It still starts overfitting from epoch 3 here, but it's less steeply than before, and we get a slightly better 89 accuracy. We can add dropout layers as well, and we get, well, almost the same performance. We can see here that dropout in this case performs slightly less well as a regularizer. So in this case, the weight regularization seems to regularize better than dropout. But yeah, the differences in accuracy are actually quite minimal. We can try to tune this, right? So in this case, we can tune the number of layers, we can tune activation functions, optimizer, batch size, learning rates, and so on. So in this case, I do a quick grid search. I vary the number of nodes in the hidden layer between 8 and 64, and I change the dropout rate from 0.1 to 5, and we see it doesn't really matter. We pretty much hit a ceiling around 89%. Right? So we probably won't be able to do much better using this representation of your data and this kind of model. What you can see though is that the more hidden nodes you have, the more important it becomes to have high dropout. Right? So in this case, if you have 48 nodes, you need 0.5 dropout. If you use 8, you can get away with 0.1 dropout. If you use 16, you need, well, it's less clear here, but there's some indication here that the more hidden layers you have, the more likely you overfit, so the more dropout you need. But it's a tiny effect. We can now look at predictions as well. So in this case, we see this review, which is from the start pretty negative. Give this a miss, terrible, terrible performance, flat, 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 and so on, right? So it fairly quickly maps to very negative score. This review is more balanced. Um, yeah, never reached the end of my satisfaction. So here you can see this is trickier, right? Because never depends on the context. And here it says, well, I feel we'll never reach the end of my satisfaction. I want to watch this more and more. So in this case, the relationship between the words matters, and we're not capturing it that well in our Beggar words presentation. So it gives, it still thinks it's positive, but it's less sure about it. We can also try the same thing with a different task. So in this case, we have topic classification. This is the Reuters dataset. It has 11,000 news stories, and it has 46 topics like politics or sport or so on. And every row is a news story. And you want to predict whether this news story is about sport or about politics or about something else. Again, so the texts are again very similar. So newswire looks like somebody, it's a weird word, so we drop it. Somebody said as a result of this December acquisition, blah, blah, blah. This is apparently a news story about finance or business, right? And so, first of all, we do the same thing. So we map all these words to an encoding. Oh, actually, these are very common words that we removed here. But anyway, we map this to individual word IDs. Again, we can then use a bag of words presentation. The topic here is tree, which probably means finance. We can again build a neural network. Same ID, so it's again a dense neural net, 2 layers. Because we're not dealing with a binary problem, we have 46 classes, so that's a particularly harder problem. So we want to have more hidden nodes. So here I use 64 hidden nodes in both layers. The input shape is still 10,000 vector representation of each newswire. Activation in this case is softmax because I have multi-class problem. Loss is categorical cross entropy, of course. And then we're done. We can start trying that. We see that, well, it gets 82% performance. It's pretty flat, so it gets better up till epoch 7, 8, but then it's pretty flat. There's some mild overfitting going on here, but that seems to be what we can do with this presentation. We can start regularizing this. We can try different kind of networks and so on. But first, let's look at if there's something else we can improve in the representation, right? So can we go beyond the bag of words presentation?